This is a video of Tom Hill and Pat Reiff in a tag team match with Vatanas Vasilianos. So I hope you enjoy it.
We've been looking at some AEC particle data from the Lee particle detector to try to see if we can distinguish two mechanisms of solar wind particle injection at the cusp. Here I've illustrated the first injection mechanism that we've tried to look at, and that is through magnetic merging at the nose of the magnetopause. Do you have a pointer? And what I'm trying to illustrate here is that if merging occurs, if injection occurs through merging at the nose, one expects a velocity dispersion of cusp particles because you're combining a parallel velocity, which brings the particles from the injection point down to the satellite at low altitudes, with an E over B convection velocity towards the pole. This velocity is the same for all the particles, and this velocity depends on the energy, so that as a result of this, one expects the highest energy particles to appear first down at low altitudes, and the progressively lower energy particles to appear at progressively higher latitudes. The next slide shows the other injection mechanism that we've looked at, namely particle diffusion across field lines in the cusp. Now, I should point out that the stationary particle trajectory kind of injection that Keith talked about generally brings particles across the magnetopause only by a few gyro radii, at least on the day side. And the observations of the latitudinal width of the cusp show that the injection mechanism somehow has to transport particles very efficiently across the field lines. The latitudinal width of the cusp is several thousand or tens of thousands of gyro radii at the least. So diffusion would be the other possible way that we've looked at of getting particles across field lines and spreading the cusp in latitude. And tried to illustrate here that if the diffusion random walk step size is proportional to the particle gyro radius, then one expects that a diffusive injection should result in an opposite kind of velocity dispersion. Here, if you look on the poleward side of the cusp, you should see the highest energy particles penetrating most deeply onto the poleward side of the cusp, the open field line region. Pat's now going to talk about some observations that relate to the distinction between these two mechanisms.
This shows the merging type dispersion that was his first case. The highest energy protons arrive first, followed by the lower energy protons. The model gives a specific 1 over lambda squared. This fits this 1 over lambda squared to an excellent degree. I have a slide which he won't let me show that resolves what the source spectrum was that produced the velocity dispersion, and it's very exciting because it shows that the source is not pure proton magnetosheath spectrum, but an accelerated proton magnetosheath spectrum. Last slide. This is what we've taken the fact that the fastest ones arrive first and the slowest ones arrive next, and we've deconvolved the original source spectrum for the protons that we saw in the cusp. And interestingly enough, this is not magnetosheath. If you say that's magnetosheath velocity, your temperature is way too high. In other words, we suspect that this is stagnated flow that had a big temperature that's been merging, has given it an alpha velocity, field line velocity that's come down. When we fit it to the lambda, 1 over lambda squared, to find out the dispersion, we have onboard convection velocity measurements. Rod Helis gave us the measurements. We were able to find the field line distance to the injection point. It turned out to be very close to 20 RE. So it's all very self-consistent. This is coming in from the nose. It's more energetic than magnetosheath stuff is at the nose. Tanis, you come?
Yes, I'm always puzzled when somebody speaks of the magnetosheath spectrum.
That's true.
In fact, the magnetosheath temperature can vary from essentially equal to solar wind velocity down to the solar wind temperature.
That's true.
And so So I can only speak of minutiae spectrum at a specified location.
That's right.
Then I have to say how one gets it, from the spider's models or
Yeah.
from what? And what do you use in your case when you say it's not a minutiae?
Okay. Well, if you look at Sprider's model, if you look at Rosenbauer's polar magnetosheath data, you either get flow velocities of a couple hundred to 300 to 400 kilometers per second, say at the polar cusp, but a temperature of only like 100 eV. And you look at proton data, and a temperature of 100 eV at a flow velocity of 300 or 400 kilometers per second is about what is typical at the polar cusp for the proton data.
But the velocity expected to be proportional to wind velocity.
That's true.
Not variably a factor of
That's
2
true.
from time to time.
That's true. That's true.
So basically you're comparing the Mach number then.
I have never seen, and I've looked at many months of magnetosheath data, I've never seen a temperature that high and a flow velocity that high in the magnetosheath anywhere.
So you'll still understand the flow velocity can be almost anything depending what it's doing in the solar wind. So the only thing one has to look for is the Mach number. And on the Mach number in the minutiae varies from 0 at the nose and down to solar wind value far downstream.
That's true.
So you can always find a place in the minutiae which would correspond to the Mach number you are seeing here. The only question is, where is that place? Is it at the nose, or is it at 10 degrees away, or 30 degrees away, or what? That's the only question you can really pose in this case.
The Mach number here is of the order of 2. I think it's between 2 and 2.5. And you can't find that kind of Mach number in the magnetosheath according to the usual flow calculations unless you go considerably behind the cusp. The Mach number near the cusp is more like between 1 and 1.5. So we're looking at plasma that had to come in the usual flow model either from behind the cusp, which is very hard to understand how it got turned around and came back towards the Earth, or else plasma from near the nose that has been accelerated through some process other than the usual expansion of the flow. And this is the point we're making.
Well, that tag team that you just saw was, thank you, was I guess the first collaboration between Pat and me. Don't give away my punchline. I'm not mirroring. I don't know why. Let's see what happens. Now I am. Okay. So yeah, that was our very first scientific collaboration, but certainly not our last. We've had many collaborations since then, not all of them of scientific nature. In fact, one of them is here today. So we've learned a lot since those days. One of the things we've learned is not to become terrified whenever Vatanus raises his hand after one of our talks. But it was also the first, the time and the place where Pat and I decided to get married, as Rick just mentioned, and as Pat mentioned. Did I do that? Too close to what? Oh, that. Feedback. Feedback, yes. As Pat also mentioned at the conference last night, there's something about Yosemite that makes you do crazy things. So it's been a long time since I've been to Yosemite. I've missed probably decades worth of Yosemite meetings, and I had two very compelling reasons to show up at this one. Not only is it our anniversary of our engagement, but it's really a wonderful experience to reconnect with the Yosemite gang and to find out what's been going on lately at the Earth. Because, as you know, I've been wasting most of my time lately on Saturn. So just a few words about people at Rice. Pat and I, of course, owe our careers to the numerous people we've run across at Rice, including mentors, colleagues, and also students that we've had the privilege of interacting with. There are just four that I want to mention here that are particularly relevant to this group. Alex Dessler was the founding chairman of the Space Science Department at Rice and got both of us really interested in the subject. He taught me lots of things, of course. One of the most important things he taught me was how to think like a scientist, and in particular how to think like a theorist, but also to bear in mind that a theorist without an experimentalist is useless, just as an experimentalist without a theorist is useless. If you only have one but not the other, then you're engaging either in mere description or mere speculation. The two have to go hand in hand to solve a scientific problem. He also taught me that a student, a recent graduate, should not be allowed to publish his thesis until he is, should not be allowed to publish his first paper until he has burned his thesis. This is back in the days where you first wrote your thesis and then you published your first paper. That's no longer true. But I actually proved that theory because my thesis never got published. There was a very clever referee, I know who it was, but I won't tell you, who found a fatal flaw in my thesis that made it not worth publishing. Dessler taught me to get over that, to pick myself up and dust myself off, and move on with my career. And I'm glad I did. So he was the founding chair of our Space Science Department. Dick Wolf was his assistant chair, I believe. And Dick Wolf not only taught me most of the plasma physics that I know, he was also very instrumental in kicking off Pat's career in space science. She came to Rice as a fresh incoming graduate student, trying to choose between the traditional physics department and the brand new space science department. Dick, I think, convinced her that she wanted to try space science, and in fact introduced her to Dave Reasoner, who ultimately became her thesis advisor, and in fact hooked her up with Dave the summer before she started grad school, where she learned a lot about data analysis. Taught Pat, for example, to look at all of the data, look for patterns in the data, but also look for outliers in the data that don't fit the pattern, because that's the outliers are sometimes where the discoveries lie. So Dave became Pat's thesis advisor. Alex became mine. Then we both got our PhDs, not at the same time, but not too far apart. She went off to Marshall Space Flight Center for her obligatory postdoc away from Rice. I went to Boulder, NOAA in Boulder, to do mine, where I had the privilege of working with Dave Evans and learning about the mechanisms for parallel electric fields, which are still being quoted today, in fact, a number of times at this meeting. Pat went to Marshall, worked with Dave Reasoner there, Jim Birch, in the group that was being run by Rick Chappell there, and got acquainted with Jim Birch, who became her mentor and actually started off what became a lifelong collaboration between those two. So I think that's it. Yeah.